So if you have harmonics on your power system and you're using a backup generator, what do you need to think about? There's a couple key points here that you have to really recognize to make sure you understand how harmonics are going to interact with generators. So, a generator, the impedance of that generator, XD double prime, is typically about 18 to 20%. And if you compare that to a utility transformer that would be on your other source, if you go through a transfer switch, that's going to be usually about 5 or 6%. So your generator has about 3 times to 4 times as much impedance as your utility transformer. Since the voltage distortion is directly proportional to what that impedance is, you're going to have more voltage distortion running on your generator. And that's just a fact of this simple Ohms Law equation. Voltage distortion equals current distortion times harmonic impedance. So ZH is either XD double prime for the generator or the impedance of the transformer. Now traditionally people used to oversize the generator to kind of, again, live with harmonics. And in fact what they were doing was, if you had a 1000 kVA generator with 18% impedance and you went to a 2000 kVA generator, essentially you were creating, instead of 18% impedance on a 1000 kVA basis, you're making it about 9%. So instead of going from 5 or 6% on the utility to 18%, you were going from 5 or 6% to about 9%. So the increase was about 1.5 times instead of 3%. And in fact, we have a demo here that I'll show you in a minute, but this is actually what goes on in the lab here. We can take and show you how that voltage distortion gets significantly worse for the same exact load based on the utility source versus the generator source. And I've done field measurements as well, where this is at a manufacturing facility, and they had about 2.3% distortion running on the utility source, and again with the exact same load they had about almost 6%, 5.7% THD on the voltage. So again, it's very noticeable. Now when you have a generator, because that system impedance is very high, you can have excessive voltage notching as well. And the issue with voltage notching is often, if you see in the middle there, where the voltage crosses through zero multiple times, you have multiple zero crossings, and you can have issues with that. So as you look at generators and you apply them on systems that have harmonic currents, you're going to get voltage distortion. How much voltage distortion depends on how big that generator is compared to your system source impedance. Now, let's take a look at a live example. And as we look at this, think about something for a minute. If you think about a generator, when you go to test a generator because you think you might have an issue, what are you going to test the generator with? A lot of times you test it with a resistive load bank. If we go back to that Ohms Law equation, voltage distortion equals current distortion times harmonic impedance. If your harmonic impedance is high, it doesn't matter what your voltage distortion is not going to increase if you test it with a resistive load bank, because your current distortion is zero. And again, that's an important piece. So let's take a look at a live example and we'll see what's going on. So what I'll do is I'll put on 4 6-pulse drives, and I'm going to run those on the normal utility source. And then after they're running on the normal utility source, what I'm going to do is I'll transfer over to an alternate source with that high impedance to show you what the generator would look like. So right now we see our current that's fairly distorted, and we see our voltage that's fairly distorted. And let's take a look at the THD for the voltage right now. THD for the voltage is about 5 or 6%. And for the current, we're about 38.1%. Now, let's go back to the waveform and look at the voltage. Okay. As we're looking at the voltage there, you can see it is a bit distorted, but watch what happens when I switch over to my alternate source. Now my voltage distortion is much more significant, and in fact I'm getting close to those multiple zero crossings there. And in fact, if I look at my harmonic spectrum, I can see my voltage distortion now is on the order of about 15, approaching 16%. If I look at my current distortion, it turns out to be a little bit less than before. So the one benefit that the generator does do is it adds some more impedance or reactance into the system, so it reduces the harmonic current a little bit in terms of the output current. But if you look at the voltage and current together now, take a look at that. We're running on the alternate source. What I'm going to do is I'm going to clean up our voltage here. And how did I clean it up? I turned off the load. So again, in fact, running on the generator would not be distorted at all if I didn't have that harmonic load. What's interesting is if I put a linear load on, like cross-the-line motors and things like that, I might get a little bit of a voltage drop, but in fact my current doesn't distort my voltage until on top of that I add in my harmonic current distortion from my drives, and now I have significant voltage distortion. So again, as we look at generators and harmonics, what's important to know? The impedance is going to be significantly higher than my normal utility source. So how can I get rid of the harmonic voltage distortion? I could turn off my load, but that's not always a great option. If I have to run my VFDs and other harmonic producing loads on my generator, I might have to filter that current so that I don't distort the voltage. And oftentimes that's the answer, is filtering the current or putting phase shifting transformers or some other method of minimizing the harmonic currents on the system so that I don't distort the voltage no matter which source I'm on.